Hello, my name is Seroka and I'm a grad student at the George Washington University. This project describes a new result regarding short-range correlations, which are nucleon pairs with small spatial separation and high relative momentum, illustrated in this figure. A recent study found that low momentum nucleons that are knocked out in electron scattering experiments have the same isospin distribution as the target nucleus, while high momentum states belonging to an SRC are evenly split between protons and neutrons. What this means for neutron-rich nuclei is that protons speed up on average. Here, for the first time, we look to see if neutrons speed up in the proton-rich nucleus helium-3. We used data from a Class 6 experiment called E2A, run in 1999, on helium-3, helium-4, and carbon targets. Recent analysis developments have made it possible to detect neutrons in Class 6. A neutron can interact with a proton in the electromagnetic calorimeter, which scatters and leaves an energy deposition. These are distinguished from proton events in that protons leave charged particle tracks in the drift chamber while neutrons don't. Along with the experimental analysis, we run a fast Monte Carlo simulation using three-body spectral functions based on the Faddeev equations. In the bottom left corner, you can see a visual of the spectral function for neutrons, as well as the acceptance maps we use to model the class acceptance. The meat of the analysis happens when we count the knocked out protons and neutrons. A set of ideal proton cuts for low and high momentum states has been developed in previous analyses, some of which are shown here. But these cuts are developed for protons, and neutrons have worse momentum resolution. Therefore, we artificially smear the proton momentum to match the neutron momentum resolution, and we find modified cuts to apply to the neutrons and to the smeared protons. The graphic in the top center shows how we select the new cuts. When trying out a potential modified cut, we count false positives, which are events that failed the ideal cut but passed the modified cut, and false negatives, which are events that pass the ideal cut but fail the modified cut. The goal is to minimize the difference between the two. The center bottom figure illustrates an example of the cut optimization for simulated high momentum neutrons. Each pixel represents a combination of two modified cuts. The white valley shows where the difference between false negatives and false positives is minimized, and the X indicates the modified cut that we choose for this analysis. This table shows the rest of the modified cuts. There are other effects that we correct for, such as the neutron detection efficiency, which we find using momentum conservation and deuterium breakup. Finally, we get to our result in the last figure. Here we measure E'(n) over E'(p). The green squares are low momentum states, and the magenta circles are high momentum states. The empty data points are from the previous study by Maytal-Dewar, and the solid data points are from our current study. The blue data points are the result of the simulation. The data in simulation for helium-3 low momentum states fall along the green line with slope of n over z. This is what we expect. For the high momentum states, we see that neutrons do speed up somewhat in proton-rich nuclei, but not quite as much as expected. NP falls short of unity, which would be the result we would expect if they sped up and we saw NP dominance like we do in neutron-rich nuclei. Finally, we see a nice agreement between the data and simulation, giving us confidence in the ability of the spectral functions to accurately model the three-body dynamics of helium-3. Thank you for coming to my poster. I welcome your questions.